Hi everyone, welcome back to Math 261. This is Scott. Let's get started. So, what we are going to be doing now is talking about section 6.3, in which we continue something that we started in 6.2, and that's the topic of orthogonal projections. Now, in particular, what we had in section 6.2 was the very limited case of an orthogonal projection onto the span of a single vector. But here we're going to expand that a little bit, and what we're going to look at is a setup where what we have is a subspace of Rn. So W is a subspace of Rn with orthogonal basis. Meaning that this is a basis for W and each of the vectors is orthogonal to all of the others. So with orthogonal basis, U1 to UP. All right. Now, Y is just going to be some vector in Rn. And in particular, it is not necessarily an element of W. That's the important thing here. So Y is not assumed to belong to W, although it might. Now, here, what we're going to be exploring are the consequences of what is called the orthogonal decomposition theorem. And that says this. So with the above setup, the setup is above. Then Y can be written uniquely as a sum Y equals Y hat plus Z, where Y hat belongs to W and Z belongs to W perp. So Y is an element of W, it is in the span of those U's, whereas Z is in the orthogonal complement to W, meaning it is perpendicular to the elements of W. And furthermore, not only can we just say blandly that it can be written this way and that way is unique, but better yet, we can constructively tell you exactly how to produce the Y hat and the Z. So in particular, Y hat is equal to, and it's going to be Y dot U1 over U1 dotted with itself times Y. So this is a scalar, so this will be a scalar multiple of, sorry, not times Y, times U1, I should say. plus, so scalar, scalar, and together they'll make a multiple of y1, plus y dot u2 over u2 dot u2 times u2 plus dot 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 up to up, oops, I mean y dot up over up dotted with itself all times up. And z will just be equal to the difference, y minus y hat. All right, let's give this a try. So here's an example. So let's say that what we have is the following collection of vectors. u1 is equal to 1, 2, 1, 1. u2 is equal to -2, 1, -1, 1. u3 is equal to 1, 1, -2, and -1. And then let's say that u4 is equal to -1, 1, 1, -2. Alright, and furthermore, we're going to have one more vector x, which is going to equal 4, 5, -2, 2. Alright, so here are our tasks. First off, A. Verify that the UI form an orthogonal basis for Rn. So basically here, what we just have to do is, since we have 4 of them in R4, sorry, I should say R4 specifically, for R4. Since we have 4 of them, what we just have to do is confirm that they're all linearly independent and that they're all orthogonal. But if they are all orthogonal and they're all non-zero, then that implies that they're linearly independent. So I just have to make sure that they are pairwise orthogonal. So u1 dot u2 is equal to, and then we'll just calculate it away. So -2 plus 2, -1 plus 1 equals 0. Check. u1 dot u3, 1 plus 2 minus 2 minus 1. All cancels out, equals 0. u1 dot u4 is equal to -1 plus 2 plus 1 minus 2. All cancel out, and that gives us 0. And then u2 dot u3 is going to be -2 plus 1 plus 2 minus 1. We're constantly getting these pairs of canceling terms. So let's see, that was this with this, this with this, this with this, this with this. Now we're going to just do that with that. u2 dot u4 is going to be 2 plus 1 minus 1 minus 2. Cancel each other out. And the only pair left is U3 and U4. That's going to be -1 plus 1, -2 plus 2. And so, since they are all orthogonal, and that means they're linearly independent, and since there are 4 of them, they are a basis for R4. So let's just put that on the record. Because they are orthogonal, non-zero vectors, they are linearly independent, and since there are 4 of them, they form a basis, and since they're all orthogonal, it's an orthogonal basis. An orthogonal basis for R4. Okay, so that was task A. We verified that we are in at least something that relates to the setup of this whole section. So now let's look at the vector x. So write x as the sum of, first off, a vector in span of u1 up through u3, and 2, a vector in the span just of the u4. So this actually is another twist on the version of the orthogonal decomposition theorem that we saw above. If we have an orthogonal basis for all of Rn, then what we have here are 2 mutually orthogonal subspaces. So we have the span of the first 3 and then the span of the fourth. And those will be perpendicular to each other. So this would be basically decomposing it into x hat and then z, which is left over on here. But we can make these in the format that is basically the exact same thing that that we wrote up there. So this is going to be x dot u1 over u1 dotted with itself. And that's times u1. Plus x dotted with u2 divided by u2 dotted with itself times u2 plus x dotted with u3 divided by u3 dotted with itself. And that's going to be the part that is in the span of the u1, the u2, and the u3. And so let's actually just go ahead and calculate that. So that's going to be, so if we look at the actual components of the u's, that's going to be, so I'm just going to bring this down so we can see it more easily. So x dot u1 is going to be 4 plus 10, so it's 14, minus 2, it's going to be 12, plus 2, it's 14. Divided by u1 dotted with itself, so it's going to be 1 squared, plus 2 squared, plus 1 squared, plus 1 squared. So that's going to be a total of 7. Alright, so then for the next one, x dot u2, so it's going to be negative 8 plus 5, so it's going to be negative 3, plus 2 plus 2. So that's going to be a total of 1. And then downstairs, so it's going to be u2 dotted with itself, so it's going to be negative 2 squared, 1 squared, 1 squared, 1 squared. So it's going to be a total of 7. And then the last one here. So we have 4 times 1 plus 5 times 1, that's 9 so far, plus 4 minus 2. So it's going to be a total of 11. And then downstairs we have 1 squared plus 1 squared plus 2 squared plus 1 squared. That's going to be 7. So looking at this, what we've got here is going to be 2 times u1 which, oops, 2 times u1, so let me see here, I'm just going to keep this part so I can see it. 1, 2, 1, 1, plus 1/7 times u2, negative 2, 1, negative 1, 1, plus 11/7 times u3, which is 1, 1, negative 2, 1, which is going to equal, and now we just crunch the numbers, so it's going to be 2, it's going to be, so it's going to be negative 2/7 plus 11/7, so it's going to be 9/7 plus 14/7 is going to equal 23/7. Down here we're going to have 4 plus 1/7 plus 11/7, so that's going to be 12/7 plus 4, so that's going to be 28/7. It's going to be a total of 40/7. And here we're going to have 2 minus 1/7 minus 22/7, so it's going to be negative 23/7 plus 2, which is 14/7, so that's going to equal negative 9/7. And then finally we're going to have 2 plus 1/7 plus 11/7, so that's going to be 12/7 plus 14/7 is going to equal, oops, my u3 here is supposed to be negative 1 down there. Okay, so it's going to be 14/7 plus 1/7 is 15/7 minus 11/7 is going to be 4/7. No, sorry, that's not right. So 14/7 plus 1/7 is 15/7 minus 11/7. Yeah, 4/7. Yeah, that's right. Sorry. Doubting myself for no reason. Okay. So this is the part that is in the span of the u1, u2, and the u3. Now, Also, we can say z, which is equal to, well, we can either think of it as being the projection onto u4, or we can do the subtraction, x minus x hat. Either way, it should be the same. So z is equal to, might as well just do x dot u4 dot u4 times u4, which will be, looking at this, we're going to have, so x dot u4 is going to be -4 plus 5, so that's 1 minus 2 minus 2. It's going to be -3, sorry, -5, actually, let me check that again. So -4 plus 5 is 1 minus 2 minus 2, yeah, negative. Oh, sorry, minus 1 minus 4. So minus 2 minus 4. Sorry, anyway, it's -5. You can check it for yourself. According to my preliminary calculation, it's -5. Yep, so -4 plus 5 minus 2 minus 4. And then down here, u4 dot u4, like every other time, it's going to be 1 squared, 1 squared, 1 squared, 2 squared. So it's going to add up to 7. Which is going to equal then -5/7 times 4 is going to be, well, here. Sorry, -5/7 times -1, 1, 1, -2. So it's going to equal positive 5/7, -5/7, -5/7, and then positive 10/7. And you can confirm that this is equal to x minus that. I will leave that to you. So confirm, check. It's equal to x minus x hat. Left to you, the dedicated student. Okay, so then x is equal to 23/7, 40/7, -9/7, and 4/7, plus 5/7, -5/7, -5/7, and 10/7. So there it is, decomposed into those two pieces. Now I could have repeated the same thing with any of the others, or I could have done it, in fact, without even having the U4. So this was a little bit, in this situation we had a little bit more than what the hypotheses of the orthogonal decomposition theorem required, and in fact what we ended up with was something that could be done in two different ways. We could have, though, found this by just doing the subtraction instead. Now, what does this all mean as far as the actual geometry of this? So geometrically, think of W as a plane. So we have a subspace within Rn. So think of it as a plane. Then y hat is the orthogonal projection onto W. So if we think of W as being a plane, and in particular, just imagine a plane going through the origin, and let's just say the way it looks is like this. So it's got one vector going out that way, one vector going out that way. Or better yet, just imagine the plane is the xy axis. That's the easiest thing. Over here. That's actually a good looking plane there. Okay, so there's W. Now we've got some other vector which is not on the plane. Let's say the other vector is going up like this. So this is Y. It's not on the plane. It's sticking out of the plane. But if we project ourselves downward into the plane, so this part right down here, that would represent the Y hat, and then this part would represent the Z. So zooming in here, so this is a cross section. So if we do a cross section that it's only focused on this particular slice of the plane, we've got a Y going this way, we've got a Y hat going this way, and we've got a Z going this way. Now, what then the Y hat represents, also geometrically, is the point on the plane, or in other words, in the space W, that is closest to the external point, Y. So Y hat represents the closest point in W to Y. Furthermore, Z, the magnitude of Z, is the distance. The minimal distance. From Y to W. Because there's no more direct way to a plane than a right angle towards it. So what that means is that what we have is a recipe for finding the closest point to a plane, and also the distance that a point is from the plane. Let's give this a try. So what closest point here means? So closest point closest point means that that the absolute value, or the magnitude, in other words, of the length of Y minus Y hat is less than or equal to the magnitude of y minus w for all w in w. So that's what I mean by closest. So if you ever see that, as a description in a problem or something, it's just specifying that we mean closest in the usual geometrical way, which means that you can't have any point that has a smaller distance than the distance between y and y hat. Okay. Now let's give this a try example-wise. So take y, which is equal to 3, 4, 5, 4. Oops, that's a y, regular y, not y hat. 3, 4, 5, 4. Regular y, not y hat. u1 is going to be equal to 1, 1, 0, negative 1. u2 is going to be equal to 1, 0, 1, 1. u3 is going to be equal to 0, negative 1, 1, negative 1. So we are not here going to be given already an u4. We are just given these three. And we'll be told that w is what we will be calling the span of these u's. Okay. So first off, let's confirm that we are in this setup that we are promised at the beginning of this section, namely that this is not just a basis for w, but it is an orthogonal basis. So A. Confirm that the u1 or that the ui are orthogonal. Okay, well, let's confirm. So it means taking a few dot products here. So u1 dot u2 is equal to 1 plus 0 plus 0 minus 1 equals 0. u1 dot u3 equal to 0 minus 1 plus 0 plus 1. Then the only other pair is u2 dot u3. So that's going to be 0, 1, 1 minus 1 equals 0. Check. Okay, so if they truly are orthogonal, then we can proceed to answer questions such as what we would have in the section, which is, we've got this y here. So let's find the projection, the orthogonal projection of y onto w. B. Find y hat. The orthogonal projection of y onto w, also known as y hat, which is projection w y. All right, so Now, if we want to do this, we are going to have to just use the formula. So y hat is equal to y dot u1. So we have an orthogonal basis, so we just use the formula. Over u1 dot u1 times u1 plus y dot u2 over u2 dot u2 times u2 plus y dot u3 over u3 dot u3 times u3. Alright, so now let's calculate these, and we don't want to write out all the details of it, because if anything, it's likely to more likely to mess us up than to help us. So let's just calculate away. So 3 plus 4 minus 4 equals 3. And then downstairs, it's going to be u1 dot u1, so it's going to be u3. Okay. Plus. Now y dot u2, so it's going to be 3 plus 5 plus 4. So that's going to add up to 12. And then divided by u2 dot u2, so it's 1 squared plus 1 squared plus 1 squared. Be 3. And then we have 3 times 0 is 0, minus 4 plus 5 minus 4. It's going to equal negative 3 over squared, 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 3. Alright, and then this is just going to be 1 times u1, so it's 1101, plus 4 times u2, which is 1011, minus 1 times u3, 0, negative 1, 1, negative 1, which is just going to equal, going across here, 1 plus 4 equals 5, 1 plus 1 equals 2, 4 minus 1 equals 3, and then plus 4 minus 1 equals 4. Okay, so there is the orthogonal projection of y onto w. Now for B, that was that, and C, let's say decompose. Y into y hat, which is in W, and Z, which is in W perp. So the perpendicular, or the orthogonal complement to W. So the y we already have, the y hat we already have, the z is the only thing left. So z is equal to y minus y hat, which is, so the original y was 3, 4, 5, 4, minus 5, 2, 3, 4. And so that's going to equal negative 2. And that's going to equal 2. And that's going to equal 2. And that's going to equal 0. So this, which by the way, this is, if you'll recall, this z is called the orthogonal complement. of y. Okay, now for the last part here, D, find the point of W closest to Y and its distance. From Y. Alright, well, we actually already pretty much have this. We don't even need to go to a fresh piece of paper for this one, but might as well. So, the orthogonal projection 5, 2, 3, 4 is the closest point. Of W to Y, and then the magnitude of the Z, which is equal to square root of -2 squared plus 2 squared plus 2 squared plus 0 squared, which is equal to 4 plus 4 plus 4, square root of 12. We can just leave it like that. We don't have to go nuts on simplifying things. So this is the distance from Y hat to Y. All right. Now, one last thing in this section, and then we will close up shop. So note. U dot U, which is a thing that we see in a lot of the denominators of the components of the orthogonal projections of things. So this is the same as the magnitude of U squared. So if U is a unit vector, oops, U dot U equals 1. Now, what that means then, if the U1 up to UP is not just an orthogonal basis, but is an orthonormal basis, orthonormal, so not just orthogonal, but orthonormal, so in other words, has all unit vectors in its set. So if it's an orthonormal basis for W, then Y hat, which is going to be equal to Y dot U1 over U1 dot U1 times U1 dot 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 up to UP. So Y dot UP over UP dot UP times UP. So if we have this, then all these denominators are just going to be 1, and so that's going to be the same as Y dot U1 times u1 plus up to y dot up times up. Oops. But if you look at the format of this is actually very, very similar to the consequences of doing basically a matrix multiplication. So if U is going to be the matrix that you make out of the U1 up through UP, then Y dot UI, this is the same as the ith entry of U transpose times Y. This is U transpose times Y. Actually, the way I wanted to word this is it's the ith entry. So this is a column vector, and it's the ith entry of U transpose times Y. So in other words, U transpose times Y would equal Y dot U1, Y dot U2, down to Y dot UP. And what that means then is that Y hat, so then Y hat would equal U times U transpose Y. By definition. So if what we have is not just an orthogonal basis, but an orthonormal basis, then this actually gives us an alternative way of framing it. Now, this is a thing that will be useful in a few contexts relating to statistics, as we'll see actually in the next couple of sections. But for now, that's just a little aside. It's not going to be a huge player in this section so much as it's going to be priming the pump for the section to come. So join me for the next episode of Math 261 when we will see how to make this work for us by turning a regular basis into first an orthogonal basis and then furthermore an orthonormal basis. So that will be coming down the pike in later sections of this class. So join me then. Till then, bye.